Assalamu alaikum class. In this lecture we will discuss graph traversal techniques. Graph traversal techniques are used for searching a graph. In tree we start search from the root node, but in general directed graph there may not be a vertex from which every other vertex can be reached. There's a possibility that there is no direct edge from one vertex to another vertex. So what we're going to do, we're going to traverse the entire graph regardless of the starting vertex. To determine which nodes are reachable from given node, two standard methods are used: depth first search and breadth first search. When a graph is given, we are interested in searching the vertices in the graph in some organized way. Depth first search start visiting a graph at some random unvisited vertex. That vertex can be given by a user. When a vertex is visited, a flag is marked to indicate that it has been visited. At each vertex V, DFS recursively visits an unvisited neighbor of V. It means we're going to use stack because recursion includes stack. If there are no unvisited neighbor, then recursion stop and backs up. So it is convenient to use stack in DFS. We will push vertex on the stack when visited first time, and we will pop a vertex from the stack when all of its neighbor become a dead end. Here is the algorithm of DFS traversal. First, we're going to mark all the vertices with -1 flag. This means that all the vertices are unvisited. Then we will start with some random unvisited vertex V and pass that vertex V into the function named as DFS. In the DFS function, we will mark that vertex V with one. This means that now this vertex is visited, and then we will check its neighbor one by one, and we will check its first adjacent neighbor, that is W in this algorithm. If W is marked with -1, that means that W vertex is unvisited. Then what we're going to do, we're going to call this function again recursively with W, and that's how it will traverse all the vertices in the graph. Now we will solve an example to get better understanding of DFS algorithm. So the first step of the algorithm was to mark all the vertices with -1. So here we have marked all the vertices with -1. This indicates that all the vertices are unvisited right now. In this example, we will start from vertex A. You can start from any other vertex. So what we're going to do, we're going to call DFS function with vertex A. So vertex A is pushed onto the stack, and then the next step within that function call is to mark A from -1 to 1. So we will mark A with 1. This indicates that now A is visited. Now we will check all the neighbor of A, all the adjacent node with A in some organized way. We're going to start from A to A. A is a visited vertex, so we will check from A to B. Is there any edge from vertex A to B? No. Now we will check from A to C. Is there any edge from A to C? Yes, there is a direct edge from A to C. And now we will check if C is visited or unvisited. If you look at this DFS number array, you can see that C is unvisited because it is marked with -1. Now we will call DFS function again. Now this time we will pass C. Till now we have called DFS function two times, one with vertex A, another with vertex C. So after the call of DFS function with vertex C, we will suspend the execution of function with vertex A, and we will resume its operation after the completion of DFS function with vertex C. So the first step to push C onto the stack, and then we will mark C with 1. This means that C is visited. Now we will check its neighbors. From vertex C to A, there is a direct edge, but A is visited. From vertex C to B, no direct edge. From vertex C to C, C is already visited. It is marked with 1. From vertex C to D, now D is unvisited vertex, We will stop the execution of a DFS function with vertex C, and now we will start executing another function called with vertex D. Now we will start executing DFS function with vertex D. D is pushed onto the stack. We will mark D with 1. Now we will start checking its neighbor. From D to A is visited. From D to B, there is no direct edge. From D to C, direct edge, but C is visited. From D to D, D is visited. From D to E, no edge. From D to F, no edge. So all of its neighbor become a dead end. Now what we're going to do, we are going to pop D from the stack and we will resume the execution of the previous function call that was with vertex C. Now we will resume DFS function call with vertex C. We have already checked its neighbor till D vertex. Now after D we will check from C to F. Is there any edge from C to F? Yes, there is a direct edge and F is also an unvisited vertex. Now what we are going to do, we are going to push F onto the stack and we will mark F as a visited vertex. Now we will check all the neighbors of vertex F. First we're going to check from F to A, no direct edge. From F to B, direct edge, and B is also an unvisited vertex. We will stop the execution of function with vertex F and we will call a function, a DFS function with vertex B. Now B is pushed onto the stack. We will mark B with 1 and start checking all of its neighbors. So from B to A, no direct edge. From B to B, B is a visited vertex. From B to C, no direct edge. From B to D, no direct edge. From B to E, yes. There is a direct edge and E is also an unvisited vertex. We will stop this function with vertex B and we call the DFS function again with vertex E. Now E is pushed onto the stack and we will mark E with 1. As you can see, all the vertices are now visited. But we will check all the neighbors of vertex E. From E to A, there is an edge but A is visited. From E to B, B is also visited. From E to C, no direct edge. From E to D, no direct edge. From E to F, direct edge but F is visited. Now all of its neighbor becomes dead end. We will pop E from the stack. Now when E is popped, we will resume DFS function call with vertex B. We have checked vertex B till vertex E. We will check B to F. There is a direct edge but F is visited. All of its neighbors becomes dead end. Now we will pop B from the stack. Now when B is popped, we will resume DFS function call with vertex F. Now we're going to check F from F to C. C is visited. From F to D, no direct edge. From F to E, direct edge but visited. From F to F, F is also visited. Now F will become a dead end and we will pop F from the stack. We will resume DFS function call with vertex C. We have already checked all of its neighbors. Now we will pop C from the stack. Now we are left with vertex A. We will check its remaining neighbors from A to D, visited. From A to E, visited. From A to F, no direct edge. So all of its neighbor become dead. And now we will pop A from the stack. This is the final output of DFS traversal with stack ordering. We have visited all the nodes in this order. First we have visited node A, then C, D, F, then node B and E.